Welcome back to The Explainer. Today, we're cracking open Chapter 6 of Peter Jaworski's fantastic book, Real-World Bug Hunting, a field guide to web hacking. We're zeroing in on a vulnerability that is completely invisible to the naked eye, yet incredibly destructive. CRLF Injection. All right, let's dive right in.
It's a pretty compelling question, right? I mean, how exactly can an invisible character break the internet? We spend so much time looking at the shiny visual output of the web, but underneath all that rendering, the internet relies completely on these unseen, seemingly harmless formatting elements. And when those foundational elements get manipulated by a clever attacker, well, the results go from a minor glitch to a complete system compromise real quick. Here is our quick roadmap for today. We'll start with the invisible web characters, then compare smuggling versus splitting. After that, we'll look at two awesome case studies: the Shopify splitting bug, and the Twitter bypass. Finally, we'll wrap up with some key takeaways for bug hunters.
Okay, starting with Section 1, the invisible web characters. So we need to focus on two very specific encoded characters today, %0D and %0A. If you're familiar with programming, you probably already know these represent a carriage return and a line feed, or \r and \n. Group them together and you get a CRLF. They're literally just the digital equivalents of hitting the return and new line keys on your keyboard. Now, here's why these matter so much. Servers and browsers rely on these CRLF characters as a strict, hard-coded rulebook. When your browser talks to a web server, it sends HTTP messages, right? Well, the server uses these invisible line breaks to know exactly where one instruction ends and a new header begins. In fact, when a parser hits two of these in a row, \r, \n, \r, \n, it knows for a fact that the HTTP headers have ended and the actual message body has begun. They are literally the load-bearing walls of web communication.
Moving right along to Section 2, smuggling versus splitting.
So what happens when a website forgets to clean up user inputs? Well, an attacker can just sneak their own CRLF characters right in, which usually leads to one of two distinct types of attacks. First up is HTTP request smuggling. This is where an attacker appends a second hidden request onto their initial one. It's incredibly dangerous because it actively confuses the front-end and back-end servers, and it often poisons server caches to serve up malicious pages to innocent users. But the second type, HTTP response splitting, is our main focus today. Instead of going after the server cache, splitting targets the client. The attacker injects new headers to literally split a single server response into two pieces, tricking the browser into executing a completely new, fake set of malicious instructions. Let's look at how this works in the wild. Section 3, Case Study, Shopify Splitting.
Back in December 2015, a hacker who goes by the handle CrankHopBones noticed a really vulnerable URL pattern over on Shopify. The URL took a parameter called last_shop, and the critical, fatal misstep here? Shopify was taking whatever text was put into this get parameter and just blindly tossing it into a user cookie on the back end. No sanitization. None.
So here's how the exploit played out. CrankHopBones injected those CRLF encoded characters, %0D and %0A, directly into that unsanitized shop parameter. Because the input wasn't cleaned at all, the server processed those invisible line breaks and literally just started a new line. But here is the absolute magic bullet. The hacker used that new line to declare a content length of 0. By doing that, the server essentially turned around and told the browser, hey, this first response, it's completely finished. Then the attacker just followed up with more CRLF characters to spin up a brand new secondary HTTP response from scratch, injecting their own malicious HTML to deface the page. It was the perfect sleight of hand. The browser was totally tricked into rendering a fake response body.
And for finding and responsibly reporting the slick response splitting vulnerability, Shopify paid CrankHopBones a cool bounty of $500. It's a great example of the real-world value in tracking down these seemingly minor formatting flaws before the bad guys do.
All right, let's turn up the heat a bit. Section 4, Case Study, Twitter bypass. So this scenario is a bit more like a heist. You see, Twitter actually knew all about the dangers of CRLF injections, and they actively tried to protect their site by setting up a strict blacklist. If you tried to inject a carriage return, Twitter's web application firewall would catch it immediately and throw a 400 bad request error. Try to inject a line feed, it would just replace it with a harmless blank space. The front door was locked, bolted, and heavily guarded.
But then, a hacker named File Descriptor found a truly brilliant disguise to sneak right past those guards. They used this incredibly bizarre multi-byte character string, %E5, %98, %8A. For context, that is the UTF-8 encoding for a very obscure Unicode character. And this is where we get that absolute mind-blowing aha moment. Let's break it down. Step 1, file descriptor submitted this weird multi-byte Unicode string. Because it wasn't explicitly on Twitter's blacklist, it sailed right past the initial security check. Step 2, Twitter's backend systems naturally decoded this UTF-8 string into its raw hex value, which was 560A. And step 3 is where the fatal irony kicks in. Twitter's logic realized 56 was an invalid character for this context, so it stripped it away, but it left the 0A completely intact. Think about that for a second. Twitter's very own security logic, its own cleaning process, accidentally manufactured the raw 0A line feed out of thin air. It basically turned the defense mechanism against itself, successfully injecting the invisible break. File descriptor used this genius bypass to inject multiple line breaks, successfully splitting the response just like we saw before. But instead of just defacing the page like the Shopify case, he escalated the impact massively. He injected a new location header hiding an SVG image tag that was designed to execute a malicious JavaScript payload. The second the browser processed this split response, the JavaScript fired off. This gave the attacker the ability to completely steal the user's authentication cookie and hijack their session entirely. Because this exploit successfully bypassed active blacklists, chained multiple concepts together, and resulted in a complete account takeover, Twitter rewarded File Descriptor with a very impressive bounty payout of $3,500. Absolutely well-deserved. Which brings us to our final part, Section 5, Takeaways for Bug Hunters. Peter Yarovorsky's guide lays out a really clear set of insider pro tips based on these hacks. First off, always proxy your traffic. You need to be watching for absolutely any place your input bounces back from the server. Second, if you ever see your input returned in an HTTP header like a cookie, test those headers aggressively with invisible line breaks. Third, if you hit a blacklist, don't just give up. Try double encoding your payloads to circumvent those basic filters. And finally, taking a page right out of that Twitter heist, always test multi-byte Unicode characters to see exactly how the server's backend logic decodes and strips the data. Because as we just saw, sometimes the server does the hacking for you. And I have to say, all of the incredibly detailed mechanics and real-world case studies we covered today are sourced directly from Peter Yaworsky's phenomenal book, Real-World Bug Hunting, A Field Guide to Web Hacking, specifically Chapter 6. It's just an absolute goldmine for understanding how the invisible mechanics of the web can be manipulated. Which leaves us with one final, provocative question to think about. We know that servers implicitly trust these simple formatting characters to structure the very fabric of the internet. So, are the invisible line breaks in your web applications truly secure? Think about that the next time you're reviewing a codebase. Thanks so much for joining me on this explainer, and keep exploring.